I'm going to assume that you already know that if I have one straight line, and with a compass, with the point on one end of the line, I draw a curve that passes the midpoint of the line, and then with the point in the other end of the line, without altering the legs of the compass, I draw another curve. The curves will intersect in two places, and if I join those intersects with a straight line, that line will be perpendicular to the blue line and will also bisect the blue line, and so we call that line a perpendicular bisector. Now we could check that the line is perpendicular by using a protractor or some other instrument, and we could check that it bisects the blue line by using a ruler. But I want to show you without the use of any type of measuring instrument that from this process we do in fact get a perpendicular bisector. So let's do that. We'll begin by marking the end points of the horizontal line, and let's examine the two curves. If we look at the curve that begins on the right and ends on the right, because we used the compass to draw the curve and the point of the compass was at the right end of the horizontal line, we know that every point on this curve must be the same distance to the end point of the line. Let's say that that distance is x, but we did exactly the same thing by putting the point at the left side of the horizontal line and then drawing the curve, which means that for the curve that starts and ends on the left, not only is the distance between any point on the curve and the left side of the line always the same, that also must be the same distance as when we did it on the right side of the line, because the compass remained unaltered. So the distance from the left end to anywhere on the left curve must also be x. I'm now going to add a few more lines to this structure. I'm going to draw a dotted line from the left end of the horizontal line to each of the two curve intersects, and I'm going to highlight the intersect points. And if we focus only on the left curve, the intersects lie on that curve. This means that the two dotted lines begin on that curve and terminate at the left end of the horizontal line, and we've seen that whenever that happens, the distance must be x. So the length of the two lines is x. And now I'm going to repeat what I just did, adding two lines from the right side of the horizontal line to each of the curve intersects. And hopefully you can see that the length of these two dotted lines must also be x, because if you consider the curve that starts and ends on the right, the dotted lines begin at the intersection which is on the curve and terminate at the right side of the horizontal line. And we showed that any line that starts on the right curve and ends at the right side of the horizontal line has a length x. So the length of both of the dotted lines is x. Now, if we focus only on the dotted lines, can you see the shape we've created? Well, yes, it's a quadrilateral, but it must also be a parallelogram because opposite sides are of equal length. But it's that special type of parallelogram where all edges are of equal length. And this special case of parallelogram is called the rhombus. And we're going to use the rhombus to prove that the yellow line is perpendicular to the horizontal line and that it bisects the horizontal line. The proofs that we are looking for can be found in the properties of rhombuses. I'm going to look at these properties in the definitions of the Wikipedia page that explains all about rhombuses. We already know what the basic properties of a rhombus are, so let's scroll down to the characterizations, and these explain the properties in more detail. The characteristics that we are interested in are on this line, and it tells us that a rhombus is a quadrilateral in which diagonals are perpendicular and bisect each other. Let's copy these properties and take them with us back to the rhombus. So we have the two rhombus properties, the diagonals are perpendicular and the diagonals bisect each other. Now if we look at the blue and yellow line, we see that the blue line joins opposite corners of the parallelogram and the yellow line joins opposite corners, so they must be diagonals of the parallelogram. The yellow and the blue lines must be perpendicular. The other property is that diagonals bisect each other, which means that the yellow line bisects the blue line. Since the blue line is bisected, let's give either side of the line a value. We'll just give them the value a. And now if we remove everything apart from the original structure, we can see that in fact the yellow line is perpendicular and is a bisector of the blue line. So this is a perpendicular bisector, which is what we set out to prove. I'll be using this concept in some upcoming proofs, so stay tuned. That's it for now. Thanks for watching.